Hi viewers, welcome back to the second segment of the second lecture of this online series of lectures on Introduction to Category Theory. So in this second segment, I will start the discussion with the notion of the composition of two functions. Okay? Composition of two functions. Given a function from x to y and another function g from y to z, where it is important to have the codomain of f to be the domain of g, okay, which is in this case the set y, where the codomain of f is the same set as the domain of G. Diagrammatically, this can be written as this. The composition of G with F, or it can be read as G after F, is denoted by G circle F from X to Z. Okay? So, this composed function can be represented by this arrow from X to Z. Now, there is this notion of onset that I want to discuss now. Let me change my marker. It's not working either. X, Y, the sets denote by set X, Y, the set of all functions from X to Y. In this context, I want to state what it means by equality of two functions. Note in this context that two functions f g from x to y are equal if and only if fx is equal to gx for all x in the domain. This is what it means by two equal functions. Okay. Now, there is an exercise here that I will try to work out. I will leave the details of the exercise for you to figure out later after the class. We are given two sets, A and B, where A is the set of the first 5 natural numbers, and B is a 2-element set whose elements are x and y. Now we are asked to find the elements of the set, or we are asked to find how many elements does set A comma B have. Okay. Recall that by definition, on set A comma B is the set of all functions from the set A to the set B. Okay, so the elements of this set are precisely functions from A to B. Now the question is, how many functions we can construct from the set A to the set B? Okay, so let me draw a diagram the two sets x and y. There are 5 elements in the set x, denoted by 1, 2, 3, 4, 5. Okay. And there are 2 elements here in the set y. Okay. So we can have different functions between these two sets. So let's take the example of the function where all the elements of x are mapped to the single element x in y. Meaning, this is the picture for the given function. All the elements are mapped to x. Okay? Alright. So, if we want to have all the 5 elements of x to be mapped to the single element of y, how many ways we can do it? That is the question. There are 2 precise ways we can do it. So this is one way. Another way is where all these 5 elements are mapped to y. So there are 2 ways. If we count all the possible ways of constructing all possible functions, there are 2 ways we can do this. Okay? Alright. So now, there is another possibility where 4 of the elements of x is mapped to one of the elements of y, and the rest of the element is mapped to another element of y. How many ways we can do that? We can achieve that in 5 to 4 times 2 ways. Alright? Now we can ask another question. If we have 3 elements of x to be mapped to one element of y, and the rest of the 2 elements of x is mapped to the remaining element of y, how many ways we can construct such a function? we can do that in 5 choose 3 times 2 ways. Okay. So these are all the possibilities of constructing function you can check, and they add up to two plus 10 plus 20 equal to 32 ways. Okay? So there will precisely be 32 functions in this set, this Hom set from A to B. Alright? So there is a cleverer way to count the number of elements in this Hom set A to B. Let me write it down for you. So the number of elements in a finite set will be denoted by this vertical bar. It actually denotes the cardinality of that finite set that we will define in a rigorous way in today's lecture later. But for now, just think of this vertical bar placed around the set to denote the number of elements in that set. Okay? So the number of elements in this set of Hom set from A to B is precisely the number of elements in B raised to the number of elements in A. So this is the cleverer way to do it. This is the cleverer way to handle the same problem. Okay? So it gives you immediately 2 to the power 5 is equal to 3. Because there were 5 elements in the set A and there were 2 elements in the set B. Okay? So we are also asked to find in the second part of the exercise how many elements are there in Hom set. Okay, so according to the way we did it for Hom set A to B, the answer is the cardinality of A raised to the cardinality of B resulting 25. All right. Okay, now some other definitions related to functions. Which is called the identity function on X. It's denoted by identity function on X from X to itself is defined by IDX acting on an element of dx to return the same element for all x. Okay. Now let's get to the notion of isomorphism between sets. isomorphism between sets. Okay, let X and Y be sets a function f from X to Y is called an isomorphism. It's called an isomorphism denoted by this is the isomorphism notation. If there exists a function besides this function f, if there exists a function g from y to x so the domain and the codomain are swapped here such that G composed with F is identity function on X and F composed with G is the identity function on Y. Where we have already defined what these identity functions on X and Y mean. Okay? So if there exists an isomorphism between two sets, we say that the given sets are isomorphic to each other. So diagrammatically, if the sets, these two sets are isomorphic, with F being the isomorphism between them, there exists a function G satisfying all these properties. So that G composed with F, meaning that it starts at F. When we are thinking about this composition of these two functions, this function starts at X. This composed function starts at X. It acts on X actually. It acts on X via F and get back to X itself, all right? And we demand that this composed morphism or the composed function should precisely be the identity function on X. All right? So this is the way to remember this thing. And how to remember this F composed with G. Let us draw it again, the diagram again. F composed with G acts on, where does it act? It acts on Y first, okay? So it acts on Y first and then get back to Y this way, okay? And we demand that this morphism is precisely identity function on Y. Right. This is the way we remember these two functions, these two conditions. All right. So this is the definition of an isomorphism. And isomorphic sets. So let me give you a diagram to quickly figure out the compose function. I should have discussed it when I discussed the composition of two functions, but I forgot. Let me get back there of the composition of two functions and give you an example for that. So, okay. So we are given three sets since we are dealing with the composition of two functions. We need three sets. Okay. Set X consists of three elements: X1, X2, X3. Set Y consists of four elements: Y1, Y2, Y3, and Y4. And set Z consists of two elements: Z1, Z2. Okay. So the function F, so X, Y, and Z, F and G. Okay. The function F is given by this assignment. X1 is mapped to Y1, X2 is mapped to Y2, and X3 is mapped to Y4. Whereas for the function G, Y1 is mapped to Z1, Y2 is mapped to Z2, and Y4 is mapped to Z2 as well. We can check separately that F and G satisfy all the basic properties of a function. Okay? This is F and this is G. So the two elements, okay, so Y is the codomain of the function F, and Y is also the domain of the function G. Okay? So what will be this function G circle F? So let me draw it here. This is X and this is Z. There are three elements here in X, X1, X2, and X3. And there are two elements in Z. One just follows the arrows. One just follows the arrows to get this composed morphism or composed function. So X1 goes to where? Z1. X1 goes to Z1. X2 goes to Z2. This way. X2 goes to Z2. And X3 goes to Z2 also. This way. So this is precisely G composed with F. Alright? Good. Now, I will state a small lemma now and try to give you the flavor of the proof of it. Alright? Let me state it first. It's related to the isomorphism of sets that we have discussed right now. Lemma 1. The following facts hold about isomorphism. Okay. All right. One. Any set A is isomorphic to itself. Any set A is isomorphic to itself. It's a very trivial statement. You should be able to understand it right away. 2. For any sets A and B, for any sets A and B, if A is isomorphic to B, then B is also isomorphic to A, which is also very trivial to prove. B is isomorphic to A. So the student should be able to prove these statements. Okay? So the first two statements are very easy to prove. I leave them as an exercise for the viewers. For the third statement, it tells you that for any set, for any three sets, A, B, and C, if A is isomorphic to B, isomorphic to B, and B is isomorphic to C, then A is isomorphic to C. So I'll only prove the third part of the lemma. Proof of part 1 and part 2 are trivial, yet I request the viewers to go with the proofs by themselves. Okay. Alright. So for the second segment, I'll finish with the proof of the third statement, and then I'll take a break and move on to the third segment. Alright? So, or it's a better idea to leave the proof for the second segment. Alright? So I'll get back to you in the third in the third segment to carry on with the proof. Thank you very much.